All right, so I've actually lost track. Welcome to lecture number 18, I guess. Around there, yeah. And we've just started to quantize, and suddenly half of the course has tunneled somewhere into quantum world. But we are recording, so you can watch it later. Let's say you have operators that phi of some coordinate and at a fixed time, and phi b operators satisfying operators that act on some vector space with a scalar product and all this stuff. If I reverse the order, nothing happens. So there's operators for every point in space. They can act here and then there, or the other way around, nothing changes in the action. The action isn't zero, but the order doesn't matter. The difference of this order minus the other order is zero. And the same with the pi's. Y. And if you take one phi and one x operator, that's one phi and one pi operator, then they produce something, very little, but something when they're exchanged. So let this be operators, and there's another operator, a special operator called the Hamiltonian or Hamilton operator. It is 1/2 this pi squared x, the whole thing then integrated, that's 1/2 pi squared plus 1/2 m squared pi squared. X. So then this stuff, these operators there in this Hamiltonian define a quantum system of particles that are uncharged and have spin zero. You don't see this yet, but that's what they do. And now you ask, where do they come from? Where does all of this come from? Well, it starts there. It really starts there. We're defining this, and that's our guess of modeling that physical system. Since it's hard to guess it from nothing, we have this procedure, canonical quantization, but there's this gap in between because there's not a derivation. It is motivated by similar looking formulas for a classical field where these brackets have a totally different nature. They're Poisson brackets and all that, but it looks the same. It is quite amazing that people massage classical mechanics so much that it all looks the same. At least I felt so in first year mechanics, theoretical mechanics. Why, after all this Lagrangian business, do I have to learn another way of writing the same thing in a Hamiltonian form, which didn't give me anything new in terms of solving problems? It felt even more awkward because you had two equations and why. And see, sometimes it's worse to have lots of ways of writing because here this is clearly very helpful in guessing this quantum theory. Well, if I had time, I would say really the Hamiltonian also, not just because of this analogy, is interesting because it allows you to make way more transformations and coordinate definitions, redefinitions than in the Lagrangian, right? In the Lagrangian, you have the coordinates and you can redefine the coordinates. In Hamiltonian, you can mix up everything, coordinates and momentum. I just wanted to add this remark not that somebody thinks, oh, Hamiltonian is boring and by itself not necessary. So but anyway, here we know it comes from this canonical quantization procedure, but really this is where it starts, and we have to check whether it's consistent. And we'll find many things along the way. In the case of the scalar field, there's the least amount of trouble. And it gets more complicated for the spinors and the vectors. But one thing we'll find that what you would think is empty space, that person here is not there, who wondered why we have an empty space state, has suddenly, if this is the real Hamiltonian, has infinite energy. Oh, weird. So we'll modify this. So really, my point is that's just the first attempt. And then when we introduce interactions, lots of other things will happen. This M, what's the M? M is suggestive of mass, right? You think this is the mass of the particle, but it isn't. It isn't always. It's just the parameter in there, and you'll have to figure out what the mass is from computing the dispersion relation, and that's the relation between energy and momentum. It's computed from the Noether charges, and we'll see whether this M or not. In fact, this will get changed into something. This will, in fact, be an infinite constant, and then it cancels some other infinites to produce the physical mass. Right? This is called renormalization of the thing. So there's lots that's going to happen from here. So if we're saying this 100 times, this is not a derivation, this is just the first case. Now, what we want to do is try to understand this at a fixed time. So we'll just solve the eigenvalue problem, H. On some states, we'll figure out what these states are, what the energies are. So we want the states and the energies, just like in ordinary quantum mechanics. And now this looks a little complicated with this integral and all these x's and these derivatives. But if you think of the x just as a label, okay, then this is, what is it? It's quadratic in p, quadratic in the phi's. I know a quantum mechanical system is quadratic in p's and phi's. P squared plus x squared, right? Or we have q squared. I guess we write x squared. And then a half, say, and a half here. And then omega squared. You know this. Do you know this? This is a, I can write an M. What does that look like? Harmonic oscillator, yes, this is just the harmonic oscillator kinetic term and the potential term, and it's quadratic in p and quadratic in axis. And now if I have many of them, then this looks a bit like this. There's a phi squared with an index. Yes.
And I have a question regarding why we're going back to the Lagrangian, because it's Lorentz invariant,
Yes.
and we is like, oh, we really want something that's Lorentz invariant, but the Hamiltonian isn't Lorentz invariant. Do we need to go back to the Hamiltonian to quantize the field? Like, I don't see the connection in my brain why we wanted to construct a Lagrangian as Lorentz invariant, and now we're going back to the Hamiltonian, which isn't.
This is in fact a very good question about the whole logic, right? It's not just the minus sign.
It's kind of confusing.
It is indeed. I think the answer is tradition and the course description. You look it up and it says do canonical quantization. Like I'm supposed to teach you canonical quantization, and that is just based on this. Hello, test. We were muted. Anyway, now it seems to be running again. And back to your very good question. Yes, there's several. I just said that there were ways of quantizing theories yesterday. And some of them keep the Lorentz invariance. They use the Lagrangian, really. That's also in the course description, but at the very end, if you have time, look at the path integral quantization. And that is, there's no operators. It looks much more like statistical physics. You have a path integral, you integrate over all field codes. This is a funny d, usually the integral looks like dx, right? And if you integrate now, it's not the functional derivative that we learned yesterday, it's a functional integral. So you integrate over all functions. And every function is like a field, is a configuration and has a certain probability to occur. And the probability is given by e to the I action. And the action is a function of the Lagrangian, right? And then it's the integral of the Lagrangian, and there's the function of the fields. So there's the one that you're looking for, the lowest invariant Lagrangian. And then if you want to compute some expectation value of something, you stick it in here. So this thing is the expectation value of this thing when you average over all possible fields with this probability. And then everything's fine. But it's a little bit different, and I don't know whether it's more complicated. It's usually, that's why I said it's the tradition, it's what's shown to people afterwards.
Okay.
But otherwise, the criticism is completely right. Like we were talking a lot about Lorentz invariance, and then we went to the Lagrangian with all this pain of the representations, and now we are breaking it.
Yeah.
Um,
Because everything, isn't everything that we derive now not Lorentz invariant?
Absolutely not, because I have
Yeah.
the 3 and this is a fixed time.
Yeah.
Here you have to do the work then afterwards again to reestablish the Lorentz invariance. So we can, once we have it, we'll perform a Lorentz transformation and see, oh, does it look the same for some other observer? And then we're happy. But indeed, this is kind of a weird way. It's like going, right? Yes. But that's what it is. This is the mostly any textbook, like the traditional textbooks do it this way, and our course description doesn't, and that's why we're doing it. Because there are also lessons to learn. Like if you skipped it, there are other books. I think Anthony Z has a book on quantum field theory where he starts with the path integral, and then you skip it. But it's nice to know, at least in the back of the mind later. Yeah. All right. Now this looks like up to this term like a harmonic oscillator with this square and square here. And they have a continuous label. This is a bit funny because this is a coupling between the oscillators, right? This is the derivative. So what it says here is the difference between phi at x and phi at the next point, like at x plus dx and at x. You compare the two. There's a difference between, like roughly speaking, right? So this is a coupling between the two. So these oscillators are not completely decoupled. They are coupled by this term. And it makes sense. You have a wave and one oscillator here, and then the next one is pulled, it's a nice field, pulled up as well. But we can decouple them by going to momentum space. We'll see how this happens. So we go to momentum space. Let's just call this Fourier transformation because there are already too many momenta. I'm writing the phi of x as an integral d3p 2 pi to the 3, and then phi of p e to the I p vector x vector. It's your honor, 3-dimensional rather than 4-dimensional Fourier transformation, keeping the broken Lorentz invariance. And here, notation, attention, this is phi hat, and this is phi hat. But that's of course not the same phi hat as this. Phi hat would be funny because, this is a different function. You can't, and usually people write Fourier transform, the tilde, but that's even for me too much decoration. It's a different function, that's not the same phi as that, and you can tell because I write the p as an argument. If this phi of p, it's the Fourier transform of the phi of x. Right? If I write, say, why am I talking about this? What if I say, what's phi of 1 or something? Then you wouldn't be able to tell, is it this or this, right? That's why people make this decoration to tell you, is it this function or that function? If there's something that doesn't look like a coordinate or a momentum, like A, you don't know what I'm talking about. Is it this or this? So this is the danger, but I will never put an A in here. Why? I don't even know what A is. So you'll be able to tell. And the inverse Fourier transform is then integral d3x phi of x p to the minus I p times x. So you integrate over x, well then p. And there's the 2 pi to the third in here, but nothing there. You need somewhere a 2 pi to the third because the integral over b, no, I have an a here, b3a, e to the plus minus I a times b. This is 2 pi to the third delta b. So that's a nice and important formula. If you just have an exponential and integrate it from minus infinity to plus infinity, here 3 dimensions even, you get the delta function of the other thing. We'll use it all the time, and that's what transforms between the two. And I have to stick in this 2 pi to the third somewhere. Some people have 3 halves here and 3 halves powers there, but this is what we're going to use. And I do the same for the pi's. So there's also pi, like this, pi hat of x, it has a pi hat of p. Same formula, same sign, same factors. So transforming the whole thing. And the first thing I want to know is what are the equal time commutation relations for those Fourier transform fields? So what is phi of p with pi of q? So that q, it's not an a, but the q, this means this is the Fourier transform field, right? It's not a way. It's the momentum, it's of p prime, say. Then I can just use what I have here. That's an integral over x for the first one. That's an integral over y, say, and then phi of x, pi of y, and then e to the minus I p times x for the first, e to the minus I q times y for the second. Now, do you remember? I guess I wanted to ask, do you remember what this is? But it's written down there. It's the non-equal commutation relations for the coordinate fields in the coordinate representation, and it's just I delta x minus y. This allows me to integrate over one of them, say y. If I integrate over y is set to x. So integral e3x and I e to the minus I p. And this is now an x, so there's plus q times.
I think you're missing an H bar.
I think I set my H bar to
One?
one
Oh, okay.
again.
Sorry.
But there is an H bar here, and so there is an H bar here. I have to be careful if I recycle all formulas where H bar has already been set to one. For example, in this Fourier transform, where is it? This doesn't make any sense. If this is the length and this is the momentum, that's not equal to, so there should be an H bar as well. So I gotta be a bit.
What makes dimensional sense?
It does make now it does make dimensional sense because P of H is an inverse length, right? The void length is H over P and then length. So if I set it, if I don't write it here, and by saying, oh, I set it to 1, I shouldn't really write it somewhere else, because then I might have, it just, it's a bit arbitrary. So let's just
Keep it to 1.
keep it for a while if you want, but well, we should throw it away. But the rest is fine. And now here I have the integral over this exponential, which just sets this to a delta function. So we have I don't like the I. I guess it's okay. We are not in, it's not the oscillators yet. Okay, so I then is 2 pi cubed. Delta, and then whatever's written here, P plus Q. Right, so this is the equal time commutation relation for the Fourier transform field, and it looks a little different. It has the I guess that's okay, because these are not the oscillators yet, these are the fields. And then it's a number which comes from the Fourier transform. I guess this is also more like a definition of the normalization here. And then there's the delta function, which isn't a minus sign. Here it's a minus sign which sets them equal. So it gives you something if they have equal position. Here it's funny, it's something if they have opposite momentum. Okay. And then the other ones, phi with phi with the momenta never gives you anything. Because phi for x and phi of y doesn't give you anything, and then with pi of p and pi of q is also 0 always. So we have this, and we need this if you want to continue with our computation. And I'd like to write the Hamiltonian, this one, now in terms of these Fourier transform fields. So I have to insert all of this in here. And the H is integral over dx, because it is. Then it's quadratic in the field, so I have 2 Fourier transforms, integral d3p, integral d3q, and then a half, everything is a half, a half, a half, a half, and now pi squared. The first one, right, in terms of p, e, the second in terms of q, and then I have an e to the I p times x, e to the I q times x. It's the same x, so both get an x, but then we're just wanting to. Plus, now comes the gradient. Let's do the other one first, it's easier, it's without the derivative. So we have plus m squared, and this is essentially the same thing, it's just pi instead of phi, so pi of p, pi of q, e to the I p x, e to the I q x. So this is now the phi square term. And now I'm writing the gradient of phi whole square term, but if I have this, I can look at it. And what do? I have to, oopsie, pi, I'm sorry. And now I differentiate with respect to x. This hits here and brings down, and I p So for the first one, you get an IP, for the second, you get an IQ. This is a IP vector, phi of P. Scalar product, IQ, phi of Q, e to the I u x, e to the I u x. Right. Now, following, I guess we could have taken the exponentials out because they're all the same. If we integrate over x, then we'll get a delta function. So the integral over x, integral dx of e to the I e x, e to the I q x will give us a 2 I cubed delta e plus q. Three-dimensional? Like this. Yeah, I do. Maybe this can go. Can you integrate over, yes?
Maybe I'm stupid, but can you explain why you just write it with a P and a Q and not like with just P?
So what do I have? I have let's look at this. Phi of x squared is what I need there. And we can even forget about the x integration. I'm just looking at one term, this way. What is this? Is this the, like naive, you'd think, okay, why don't I write the pi squared, the phi squared, right? And then integral d 3 p of e to the which sine what? Does that make sense? That would be just writing p for both factors. Is the Fourier transform of the square is the what? The square of the Fourier transform, basically. That would be, so let's see. Is the integral, I mean, what it is for sure, phi e to the I p x, and then all squared, right? Because the phi of x is defined as this, and if you square it, then this is squared. But can I easily pull this square inside? This is what I'm doing basically, pull this inside, and that doesn't really work. You know, it's binomial formula. You have to keep it differently. In the second factor, so I can write the second factor again, and just not to get confused, I call this q by q e to the I u x. I think it would still be fine if I write p here, because I know this integration stops. There I integrate over p and there over p. But if I don't want to get confused, I call this differently, and this is my q. And now I can also move things, the q front, and then have different arguments. If here, if you like something else better, let's say what is well, if my phi, this phi, it's an integral, it's a sum, right? It's a sum of something. Let's say it's a sum of, I don't really know what, AIs, right? What is phi squared? It's not sum of AI squared. Oopsie. No, it is phi squared is the sum of AI squared. And what's that? Then we have IJ, AI, AJ. What's the difference? Here it's just the square terms and there's all pairs.
Just like use it as a helpful variable change.
Hmm?
You use it as a helpful variable change to like write it easily.
I use it as a help, yeah, well, it's more than helpful. If I didn't do it, if this was a P here, it wouldn't just be not help, it would just be plain wrong. Because I'm missing all the like off diagonal terms.
Ah, okay.
Yeah. It boils down to, it is A plus B, which I see in this beginner math, every time I see this, right? And I go, but writing here, the P is essentially this, but totally in disguise. It's the square is outside and not inside the integrand. I need this kind of, need this blackboard. And now, we do this integration over x and let's get rid of q and set q equals, so this sets q equals minus p, and the 2 pi cubed takes away this. So all of this is gone and the q is minus p. And then we have h integral p, p, that's left. And then you have, and then there's pi of p, and then there's pi, and q is minus p. And then we have plus, we have I times I, but this is a minus p, so it's actually plus indeed, plus p and squared, and then plus m squared, phi of p, phi and minus p. And that's it. That looks pretty, hopefully. That looks kind of pretty. It's not our Hamiltonian written in Fourier space. And the derivative is gone and has been replaced basically by this p squared. And now we have even more our harmonic oscillator with p squared and x squared. Okay, well, there's a little bit of a minus sign, what's going on here, but we'll be able to deal with it. Here, this is the first hint, maybe I had the hint before, that the real scalar field is just very many harmonic oscillators. So it really is just, it makes sense, right? You have, oscillator, they can also, with little masses say, and they can oscillate. This is my field theory. And that's here the spring constant, and this is this is the inertia. I guess this is what is that thing? This is spring constant, yes. And because it's here. And well, this is the coupling between them. And in the momentum space, you have the same thing. Now, this whole thing is the spring constant. Let's give this a name. Let's call this what we always called it. Let's define EP as the square root of t squared plus m squared. This is our favorite dispersion relation, right? And this square of this is here. So the energy sort of something is this spring constant in this huge set of oscillators. And you have for every p, you have an oscillator. You have in this p line, you have a coupling somehow between p in one and p in the other direction. So it's not really completely independent, but you have pairs. But it looks still very, very similar to an harmonic oscillator. And what do we do for the harmonic oscillator? We factor this thing into a product. So this was, here it's a sum and we want a product. And these terms were, yes,
I don't think I understood the analogy why a scalar field is just a lot of harmonic oscillators, just that at every point you can go up and down, and that's kind of your
This up and down is the value of the field. So it's not a direction in space, but it's sort of the value of this field. And this is indeed space. And
What does one exactly mean with the value of a field like that?
what's the value? It's just the value. This is go back classical. When they're not operators, or when they're operators, I have no idea.
Amplitude, also halt.
Yes,
Okay.
yeah, just how much. You could, of course, think that, oh, this is my z component of something really in physical space, but we don't have, we have a three-dimensional space, and everywhere there's like temperature. Phi is now the value at this location, your temperature. And the temperature can change according to some rules. And here, the dynamics of this turns out to be, it just oscillates around zero. So it's a bit funny, temperature. It goes plus 2 degrees, minus 2 degrees, plus 2 degrees. So this is your oscillation. And it also depends on what your neighboring temperature does. This even makes some sense. And then, yeah, there's this coupling. And here we factored this into 2 bits, and this was roughly I pi plus x minus I pi plus x with all these constants in there. And then this was the creation and annihilation operators. And I want to do the same thing, just in inspiration from here. Because then I can easily diagonalize and solve my eigenvalue problem. So let's write this. V3p 2 pi to the third. Here, let's see what goes in here. I want to pull out the pi of t and 1 phi. Okay, so this times and now minus I pi p, that's bad because the second is a minus p, so it's minus p plus e p pi minus p. Boom. So this is my first try to write this. It works really well if everything commuted, because this and this, the first and the first, the pi with the pi gives this pi squared type thing, pi of p and pi of minus p. The I and minus I give 1. So that's this term. And the last two together produces all of that. Like e squared is exactly this. So they work, just as it worked in a harmonic oscillator case. This times this. And the middle term naively cancel because this one with this, like the mixed term, this with this is I pi of t, and well, it doesn't work at all. It not only, oh, then we have an e p phi minus p, that's this one, and here it's the opposite order, and worse, there's the p and the minus p. I think I can deal with p and minus p. What's the other term? The other term is p phi of t minus I pi minus p. So they want to cancel because it's the same with different sign, but we don't let them cancel because if you turn them around, then we get something, right? Why do they want to cancel? This argument here is a minus sign, and there it has a plus sign. But we can change our integration variable and integrate like backwards along the p-axis, and then we have to substitute p for minus p, and say we do it here. Then we'll have a minus there, a plus there, and here in this e. It luckily doesn't matter because it's squared of pi. So when we'll do this in the future, we'll change from p to minus p, and we never need to worry about the energy because it's quadratic in the momentum. It doesn't matter if you go left or right for the energy. So this really wants to cancel even with the different arguments, but it doesn't because it's different order. And we know this from the simple harmonic oscillator in quantum mechanics. What we do is we write the same thing in a different order again. And we basically symmetrize, and that's why I didn't write my 2 here. There was a factor half, and when I write 4, I write it twice, and once in one and once in the other order. And the second order takes care of canceling the thing. So plus, and now this comes first, minus I pi of minus p plus p phi minus p, and then this one, I pi p plus p phi p, and parentheses, and then the square one. So this is I guess the same as that. Finally, it didn't work at first, but let's try it if it does actually. So let's just go back and like check. This thing is equal to d3p. Not going forward in my derivation, I'm going backwards. I want to multiply it all out. So I have pi of p pi minus p. That's the square term. Now the other one plus p squared phi of p phi of minus p. Then let's do the squares down here, and that is the same. This together, no, it's not the same because this is pi of minus p, and this is pi of p. And here, p squared pi of minus p, or phi of p. But it's almost the same. You can either do the change of integration variables, or you just use that they commute because they are just pi's and they commute. And so this is the same. So we get twice the first roll, which will cancel the extra 2 in the denominator and then makes it a 1/2. And now we have to make sure that the mixed terms cancel as I wanted it. So the outer one is plus I e p pi p, there's so many pi's and p's, phi minus p. It's these outer, and they should go away with these outer, minus I p pi minus p phi p, and then we have the inner with minus I e p phi p pi minus p, and this inner plus I e p phi minus p and pi p. It's very lengthy. And indeed, they cancel with the minus sign, they cancel with a different sign. The arguments of different signs don't matter, as we just said. So this goes away with this, and this goes away with that. And these two add up to twice as much as the first row, gives you a 1/2, and that's what it is. So check, passed. Then this is our new object, factored. So now I'm going to define the ladder operators, creation and relation operators, and hope that this is all going to work out. So let's define alpha of p. Let's just pick this. I pi p plus dp phi of p. Now you ask, how do I know? Well, how do I know that this is alpha and not alpha dagger or this or some other combination like the I here? And in fact, I don't really know. You could go back and see what we did where the signs and factors went for the simple harmonic oscillator and then try to copy it. But you can also just do something and then continue with this and figure out at the end, oh, wait a minute, what I have called alpha is really the creation operator. I should have called it alpha Decker. And that's in fact what happened to me yesterday or 2 days ago. It was all different and it didn't come out as I wanted it. And so I went back and fixed it up. You don't know in the beginning, but I don't show you the wrong computation and fix it up later. So this is, yeah, I just want to make you feel better. How would I ever know? You wouldn't know, I guess. Maybe you would, I didn't. I'm making this definition because this is what will work in the end. But when you first try it out, you just have to give it some name and see what this really is, this object. Now, this is the first factor, and what is this other factor? This looks so very different. It is not the complex conjugate because, well, here this plus I goes into minus I by complex conjugation, but the complex conjugate, there's a different argument, and there's no dagger here. However, we're working with the real field. So our field phi of x is as an operator permission, the real field. So this implies something for our Fourier transform field. The phi in Fourier space daggered. This one daggered, it's here, is equal to d3x phi of x e to the minus I p times x, all dagger, right? This is by definition. And then dagger this thing is equal to d3x, x is real. This is an e to the plus I p times x. And this dagger is the same as undaggered. So I can just leave this dagger out and have this. But that now is phi of minus p. So funny, the one that is negative here is really the complex conjugate, the Hermitian conjugate of the one with the plus argument, which is cool. Then the alpha dagger of p is the dagger of this, which is a minus pi. Pi dagger is pi of minus p plus, this is the real energy, and this is phi, and there's no hat, phi of minus p. And this is exactly the other person there. So our H in this definition can now be written as 1 quarter, this is a quarter, and then this is alpha of p, and the other factor is an alpha dagger of p, and the second line is the reverse order. And that looks very reminiscent of the simple harmonic oscillator in quantum mechanics with this a dagger. So they are probably Grayson and Laken operators. And now we have to check whether they are. First, we need to know what's the commutation relation between these guys, the alpha and the alpha dagger. Alpha with alpha is I was going to say obviously zero, but it isn't. Because, well, which one do you want to see first? Alpha with alpha, because it's different arguments. it could leave us something. Let's do this one alpha with alpha and see that this is really zero for all. So I insert this thing, right? So it's I pi of p plus EP phi of p, comma, and now the same with q. Phi q. Then did I erase it? I just erased it. See if you remember. What is pi with pi in momentum space? What is pi with pi in coordinate space? The equal time commutation relations. Zero. Yes. Even in momentum space, it's just zero because the zero times whatever, it's still zero. And phi with phi is also zero. So the only thing we have to worry about is the first with the second and the second with the first. So this is then I Q pi of t. Why is this happen? Somebody got promoted. So this is now this first term with the second term, and then we have plus I of plus I EP of then the second term with the first term. Now this is a little harder to remember. What was that? What was this? The canonical order. Do you remember?
2 pi squared.
Pi.
Delta from Q is PQ.
It was 2 pi cubed. Then we had this. We had an I and the delta function. And what was the argument?
Q.
Plus, exactly. P plus Q. Okay, and now then this, what is this? This is the opposite order, right? So it's not phi first, so we have a minus sign. That's important. This is going to save us here, this minus sign. Then we have I 2 pi cubed delta, and again the sum Q plus P, but Q and plus P is the same as that. And now here, what's wrong with EQ and EP? Does this cancel or not? I want 0. Is it 0 or not? Everything is the same except for there's an EQ and there's an EP.
That shouldn't be a hat, right?
That shouldn't be a hat. Where?
And
Oh, this shouldn't be a hat. This one got promoted too. This is not a hat, yeah.
Doesn't the delta function act on the e's?
Yeah, because there's a delta function. Everything is 0 unless the Q is negative of P. So I might as well replace this Q by minus P. But E of minus P was the same as E of P, so they are the same, except for this minus not 0, yes. So that's good. They actually commute for all arguments. It wasn't entirely clear until we did the computation that it all worked out with all the signs. Like, say if there was a minus sign or there's a minus sign, then it would have collapsed. Now, alpha with alpha dagger. Oh no, easier. What do we need? We need this. We don't need everything. Check. From there, we can easily figure out what the dagger version is. Like, what is dagger with dagger? This is the same as alpha. Now the Q one, Q and the P in the back. Dagger, right? If you dagger the product of operators, you dagger each factor and reverse the order. So if I want to know what is alpha dagger, it is the same as alpha with alpha, but then the dagger out front in the other order. But this commutator is zero all the time, so it adds zero as well. That was easy. If both alphas commute, alpha daggers commute too. The mixed ones may be different. P with Q, and there's a dagger. Now, it looks very much like that, except for, I have I P plus P phi P, comma, and now the other one that is minus I pi minus P plus P phi minus T. Boom. Now, P with pi with pi is nothing, pi with phi is nothing, so we need mixed ones. First and second is IEP, and then pi P vector with phi minus P minus, where's the Q? Sorry. I have to have different. Q, so minus Q. And the inner one is minus I P phi P I minus Q. And now what you just told me again, this thing is I 2 pi cubed delta. And now it's funny, the sum of the two momenta, but the sum is the difference, basically. The sum of the argument is the difference of the momenta.
Left not EQ.
Why is it not? It's just because I happened to know this too late. Thank you. Yes.
And now it's
What? No, this is, you're confusing me, I'm sorry.
confused.
Wait, this was the outer, and that should be a Q. And this is the inner, so that's the P from here, and that P is this P, okay?
Yeah.
This goes here, and that's that. You know, somebody complained there were so long computations when we did the Lorentz symmetry and the transformations, and this is just the scalar field. Now, the first one is minus I, because the other order, 2 pi cubed delta, and now minus Q plus P. And then we have, then it's beautiful. So then we have alpha P, alpha dagger Q is equal to I times minus I is 1. Then we have a 2 pi cubed, and we have an E, but Q is the same as minus P. So I will write P because I like P. This is my prejudice again. And then this one is the same. So I get a factor of 2, and then we have delta minus Q. So there. We have dagger with dagger is 0, always. Non-dagger with non-dagger is also always 0, and then the mixed ones is like an identity. What did we want to find, really? For the simple harmonic oscillator, the number operators is always something one, right? Or if you have many I, J, then always the ones that go together. And that looks pretty good. You have oscillators. We have alphas labeled by P. And then we have alpha, the Hermitian conjugate, still labeled by P. It's just the same thing, just conjugated. And for different labels, they commute. And for the same label, they give essentially one, or don't they? It's not so bad, except for this junk. This is okay because it's just a normalization. And some people prefer this, so let's have it here. You could also divide it into these things. This is a bit of a funny term because it depends on the momentum. Also, that isn't the worst thing in the world. You can also divide it away because they depend on the momentum. So if I divided this, that's okay. You could also leave it there. There's some reason which is not clear right now that this makes sense in a relativistic normalization. For us, we don't know what this means, so we want to get rid of it. It also gives these things a dimension. They have no dimensions. Alpha with alpha is one. They are dimensionless things. They just count. These don't just count. They have to. They have some energy. Actually, the alpha here has a unit of square root energy, right? These things, because the unit from here and there should be an energy. And so I don't want that. So let me define A of P is equal to 1 over 1 over yes, 1 over 2P alpha P. So we redefine our oscillators after all. They will show up later again, so I didn't mind this. But now we're going to use this for a moment. Yes.
With delta functions, it still wouldn't be dimensionless, would it?
Right. You're right. But with the integration, it will be, yeah, it's not really dimensionless, but it is when you integrate over it, then you're totally right though. It is, well. It's not that I wanted dimensionless, I wanted so that they count. Yes, I want their. What I want is that alpha P P3P. This should be dimensionless. This is it counts everything. You know, this creation annihilation combination thing. This counts. This counts how many excitations are there in the state with label P, and then I ask for all the P's. And so this thing also has a dimension, and then I'm very happy with this three-dimensional thing, so that it solves up this three dimension. Now here, what does that mean? Where's our Hamiltonian is up there? So the Hamiltonian H, in terms of the new oscillators, just redefine, you will get a square root 2e from here and from there. It gives you a 2e, and there's a half, so a quarter, so it gives you a half. So this will be EP half alpha. Let's write this at A. Let's write this one first. A dagger of P A of P plus A of P A dagger of P. Boom. So this is the new form. And now it dimensionally makes some sense. You know, the dimension here and here cancels. This gives you a number, and here's the energy, which is the right unit for H to be an energy. And let's just keep here for reference the P with the dagger a dagger is now just 2 pi cubed delta P minus Q. So this is what we got. If you look on the first page, there was a Hamiltonian given in terms of the operators phi and pi. And now we have transformed them. Maybe we can write this down as well. The A of P is equal to 1 over square root 2 P, and then we had an I pi P plus BP psi of P. So this is what we start. Oh, and then we have a Fourier transform. We started with this, find them, and then we have this oscillator and this Hamiltonian with these oscillators. I guess to find the states and all of it for completeness, we should really show that these oscillators raise and lower the energy. What's the time? 23. I have spelled this out in the lecture notes, and it's kind of obvious. So I'm going to spare you this computation. If you have A H with a dagger of T, what should that be? Let's say we compute the commutator rather than this. What's that? What do you think this should be? The commutator of our Hamiltonian there with one of them, with the dagger. You can compute this because you know the commutation relations here. You just take it and do your thing. But what do you think should come out? H with, but what does raising the energy as a formula mean? Like, yes, this raises the energy, but what is the mathematical expression for that idea? EP a dagger. EP a dagger of P, exactly. Because now, if you have an eigenstate of H, then a dagger onto that eigenstate gives you the original eigenvalue plus this EP. We've done it. And if there's no dagger, H, A, no dagger, what do you want? Minus the same thing, and then you know, oh, it. And I was going to write this all out, but it's long and boring, and it's written in the notes. And this is the answer, and you've already guessed the answer. So this is what comes out, and confirms that they are creation annihilation operators. Now, interesting also is that H is positive definite, which means if you take anything and sandwich it, sandwich the H, so this thing, that's always larger or equal to 0. And so let's put these two together. If I have now a state from the left and a state from the right, well, let's write it. Integral d3p 2 pi to the third d half, and now here sandwiching a dagger p a p psi and then plus psi A P A dagger P psi. Ooh. But this thing is the emission conjugate of this thing. So the whole scalar product is equal to the norm of this state. Where? So whatever state this is, it is some state, and this could be the zero state, is the norm of it, and they're always positive. So this is positive. And that's a norm of this state. So that's also positive or zero. And the energy is positive or zero. And so it's all positive. And so this thing, H is a positive definite operator.
We don't have a problem with negative energies and whatnot anymore.
No, we could see this kind of before because it was all the sum of squares, but now we see it again. We don't have negative energy problem. Exactly, we have negative frequencies. We don't see frequencies yet because all at fixed time. There's no e to the next week. We'll do the time evolution and we see things in time going clockwise and anti-clockwise as a phase, so positive and negative frequencies, but all excitations have a positive energy. The ones with the opposite unexpected frequency, the negative frequency ones, which used to be called the negative energy state, are associated with antiparticles. They go the other way in that frequency space, but still with a positive energy. So it's all really beautiful. And now we know the oscillators of A and A dagger go up and down the ladder, and the ladder has a bottom. Because H is positive definite, so it best can have zero. And so we define the bottom. Let's say we have a state which we call the vacuum. So let zero ket satisfy A of P equals zero for all P. So they are all as a set of lowering operators, and for all the P's, we want this to kill us. So there's nothing in there. This tries to take a particle of maybe P away, but there's nothing, no matter what P you use. For all P's, there's nothing. This is equals zero. So that defines this. And it should exist because if it didn't, then you could lower and lower and lower, right? You have something you lower again and you lower again. At some point, there must be some state where you can't go lower, so the lowering has to kill it. And whatever it is that it kills, we call it, give this name, called the vacuum. The energy of the vacuum. Guess? What's the energy of the vacuum? So there's nobody there. I just want to hear it. You don't have to be right. I want to hear zero. I offer zero. I propose the vacuum has energy because there's nothing, right? And let's compute it. How do you do it? So with H on zero, right? That shouldn't be too hard. What's the eigenvalue? It should be an eigenstate. So then the H is given there. It's integral d3p 2 pi third dp half, and then a dagger p a p plus a p a dagger p, all the decorations on zero, and this indeed kills it, but this one doesn't. I want to act with this A onto the zero to kill it. So we'll have to bring all the annihilation operators to the right because then I can use it. So I'm moving this to the right hand side using this one, the commutative relation. So if going to the other side, so it commutes plus something extra. So this is equal to A dagger T, A T, so the other order, plus 2 pi cubed delta and what? The difference, T minus P, that's 0. 0, three-dimensional. And now this A on 0 and this A on 0 gives nothing, but this extra term remains. And then we have the pi's go away, so with integral d through p, p half, and nothing much, delta 0. So this thing here is our energy. This is E0, the energy of the vacuum. And how much is it?
M half.
Right?
M half.
M half.
All right. What if you use the delta function for the integrand? Then we say.
Yeah, the thing is, there's no argument in it anymore. It sets something to something else, but now there's nothing. It's just bad, how the delta function looks at, we are physicists. The delta function looks like this, right? Delta of 0. At 0,
Infinity.
it's infinity. So this is basically infinity cubed, and then we have to integrate. So if you ignore that, it doesn't get any better. So if you ignore it even, then this will kill us because the energy grows with momentum, right? The energy is this function. And so then the area underneath it, three-dimensional, this is the worst thing ever, right? So this is infinity. So our vacuum, the one with the lowest energy, has not the highest, it has the lowest energy, which is infinite, and everyone else has infinite plus something. The next one, so the ground state basically is E0 equals infinity, and then if you raise it, like you act with your favorite momentum, whichever, call it E star. Yeah, I'm trying to say pick a specific value for the momentum, then you raise the energy to your state is then this infinity plus P star. Right? So it all sits up there at infinity because of this thing. You always have we have figured out the distance between the states because they are just spaced by this. Depending on which momentum you introduce to your system, you have a different spacing, right? You can have a very slow particle, you introduce the very little energy or much or whatever you want. But this is some finite number for any p, any finite p. But it all sits on top of this large ground state of this vacuum energy. And that just doesn't make any sense. Why would we bother adding everywhere this infinity? It just makes it awkward. So let's throw this away and just deal with the differences. The story goes, experimentally, you only measure the difference between things. So there's nothing here. You set your energy meter to 0, and then someone comes in, and you have a new energy, and you read it, and you get the difference between the two situations, and not from some non-existing state to the vacuum. Right? With respect to what? We measure everything with respect to the vacuum. So this is our first renormalization thing, basically. This is the first thing where we do stuff that wasn't clear when we canonically quantized. We'll just what do we do? Well, let me still say what the reason is. There's two reasons. There's a reason for this and there's a reason for the divergence here. The reason for this thing is that we have oscillators, they're close, a continuous set of oscillators. There's this delta function rather than a conic delta. If they are the same, it's just one. If you have oscillators that are spaced a finite distance in whatever variable you count them, say momentum, and then an individual is just one thing. But since they are so dense, you get an infinity here. You can also blame space for it. If you say you have a finite space and you put oscillations in there, so how many more can you then have, and then you can count them. And when the space becomes infinitely large, then become dense again. So you can also say this is because space is infinitely big. If we were in a finite space, we wouldn't have continuously many momenta, then it would be just quantized by the boundary conditions, and then this goes away. So that's that problem, that the gaps between things are shrinking. And the other divergence, this comes that it doesn't have an end. We can have arbitrarily fast, not arbitrarily fast, arbitrarily high momenta in our system. So this is the reason why it's there. But whatever good or bad reason there is for it being there, we don't like it, we throw it away. And how can we throw it away? It happened because there was a creation operator to the right of an annihilation operator, and moving it through brought us this pain. So what we're going to define now is a procedure called normal ordering. So define normal ordering operation, which says here, definition by example, or n of creation and annihilation ops, so product of creation and annihilation operators. Then you have this normal ordering operation that acts on it, and what does it do? It splits it up into first the creation, all go first, times all annihilation ops. So they just separate them. Let's do an example. Example. If I have n of this, for example, a of P1, a dagger of P2. What is this? This is a product of creation and annihilation operators, and it sorts them so that all creation operators are to the left of the annihilation operators. So this is equal to, by definition, a dagger P2, a dagger P1. It just orders them. So what this thing really is a P1, a dagger P2 really is the other order. But then plus whatever this thing says, 2 pi cubed delta P1 minus P2. So this object is this, but the normal ordering says just allow yourself to move them wherever you want. I mean, wherever they say all the creation to the left of the annihilation operators, and do not add on any of this. Don't use the commutation relations to reorder them, just reorder them. Okay? Ignore the and that's the procedure called N, normal ordering. And sometimes it's also written by colons. So this is also written like this. A P1, A P2, colon, if you don't want these big parentheses, you, oh, it's the same thing. It looks a bit funny, it looks like you defined them, but this is the normal ordering symbol. Let's make them really big. And now our H with normal ordering is basically ignoring that infinite constant there. So if we inserted these normal ordering signs into our Hamiltonian, it just means this one is normal order. So then leave it like it is. This normal order, so other order without any delta of zeros. And then the two add up, and then we have just this. Integral d3p 2 pi cubed p a dagger p a p. There it is. This is now our Hamiltonian of this quantized system with this modification that we've gotten rid of the vacuum energy. Now the vacuum really is at zero and all the others are on top, and we have the spectrum A dagger P1 to A dagger Pn on the vacuum is an eigenstate, has energy some I from 1 to n. So this is basically the answer that we were looking for. So, you know, these are the combinations of our fields, phi and pi, that we had in the beginning. And with them acting on this state, which is defined in this way, you can build up the entire sort of Fock space. So the Hilbert space there is a Fock space because it has a basis in terms of these excitations, which you count and add more. And yeah, they even have the statistics of bosons because they commute the all. It's automatically symmetrical in the way. This is the question.
Yeah, I don't know. Can you explain again why we can, because we derived the commutator of the two of A and A dagger, and now we basically just said this is zero for the normal for the normal ordering operator. Why are we allowed to do this? I didn't just.
That's also a good question. Because what does it mean allowed to do it? We had the H in the beginning, and that's what it was in the beginning, and this has the infinite ground state energy. And now we say we don't like it, so let's define the new one. I should probably put a prime there. So I'm not allowed. This is the answer. It isn't the same H. It is a new H. I say this is my improved H, a better one. This is the one I want to use now. The other one was the first guess, and it did produce this infinity. So I'm modifying it. So this is something new. So it's H prime. But it's not, I mean, completely disconnected to what we said before. It is the H that we had normal order. So maybe we can learn a lesson for other operators in other systems. Maybe we should use the classical expression for my charges. This was the energy. And then insert the fields with the hats, like the operators, make a operator for the quantum system, but possibly add the colon, so always normal order, or do something. Right? If I had time, but I don't, I would be talking about the momentum operator. In the momentum operator, P, which so the classical momentum charge is integral pi gradient phi dx. So this is the momentum rather than the Hamiltonian. The Hamiltonian was, what we just did was a little harder than that, in fact. Just now we have integral pi squared plus the other things. And then we studied this operator. The quantum operator was gotten by just put hats on it. And if you now study this one, we also want the quantum operator, so we put hats on it. But here is the first question. The pi and the phi, they do not commute as operators. So should I keep this order and put hats? Or should I first, before they have gotten the hats, move them around? This is totally equal to this when they are fields, normal classical fields. And then I put hats here. And now this second line is different from the first line because they do not commute. And when you commute them, you get something. So it wasn't really clear what order things have to go into. It wasn't a problem for the Hamiltonian because it was just squares of things. But here it is. And so generically, you always have the question about which order should you write your classical thing in so that the quantum is what you want. And now maybe it is that you always have to kind of normal order it. Because that normal ordering makes all the backgrounds within the zero. That's a pretty cool thing. So yeah, it isn't allowed, it is defining something new. If you define something new and better and
So A and A dagger are the same, and we redefined Hamiltonian to.
that's what we did. We didn't drop the extra bit. The commutation relations are still what they are. We redefined it. You could also say this is equal to what we have minus E0. That's really the same thing, except for this looks a bit more sophisticated. And what does it mean, infinity minus infinity? And so, well, this is the same thing, but it looks more sophisticated. This is really obvious. Yes, very, very good question indeed.
Doesn't this give us two options for H prime? Because we also could have just said, we could have reversed the order of the first argument. And
Yeah, that would make things worse. Then we would get a factor of 2 because then we have this thing twice. We want the annihilation first because when they hit the vacuum, they disappear. If you have the creation coming first, then it doesn't disappear. So then,
no, it's just like, doesn't the normal ordering operation always give us two?
Inside. You meant here I could have done this.
Yes.
With the normal ordering, no harm done, right? Yes.
Exactly. So we always have two solutions from, or at least two solutions, like depending on how complicated our Hamiltonian is, of new prime Hamiltonians. Because this way we would have ended up with a.
Well, here I don't have my columns anymore.
Exactly, and if we reordered the first term first, then our new H prime would be A dagger, A dagger.
Would never be a dagger. Because whatever you do inside the columns, then when they hit, they order them as they're supposed to. So the creation always goes to the left. Yes. For that reason that it kills the vacuum. I'm expecting a question, what if I have 3 creation operators and 1 annihilation operator? Then I don't know what to do here because they all go to the left. Do I keep the order? Do I mix them up? What do I do? And the answer doesn't matter because they commute. So it just has to separate annihilation from creation and the annihilation to the right and the creation to the left. But what happens in this group and their group is totally irrelevant. And if one is completely missing, then this doesn't do anything. If you have 10,000 creation operators, then it's just what it is. Yeah. Well, time is up, I guess. Well, for the homework, just look at there's nothing really more that we haven't covered. In the homework, you do the same thing for the complex field. So just copy everything and for the real and the imaginary part, and then you have the answer for the complex field. Well, I wanted to discuss the complex, I wanted you to discuss it because then you see electric charge. Here is our spectrum somewhere here. This are creates a certain momentum and energy. But if you have a complex field, then you have creation of radius A and creation of radius B, say. And one creates particles with positive and one is negative charge, and that's kind of neat to see in that's the homework. But I have to upload it.